Okay, I'd like to introduce the next speaker, who's Rewa Rai from Professor Nitin's lab. She will be talking about spectral and imaging features in leaves to predict grapevine red blotch infection. So push F5, load it up.
So thank you and good afternoon. So as he said, I'm going to present on behalf of my PI, Dr. Nitin, and he's also available here at the backside, and he will help me in person to answer any question that I will not be able to answer. Yep. So as Christian said that we are working on some sensing technology that is very required and that can be used to detect the grapevine red blotch virus infection in the field, in the vineyard. So here we are at the early stage of this discovery, but I'm going to explain why we need this kind of technology and what to do or how we can develop this kind of sensing technology. So we are currently working on the spectral and imaging features of leaves that can help in prediction of these kind of infections. Okay. So as we know, these infections, they reduces significant amount of the berries yield and also the key quality parameter of wines, that is sugar and anthocyanins. And the most limitation is these leaf roll virus infection symptoms is very similar to another virus disease, that is leaf roll, and it's hard to predict at very early stage that this is the red blotch infection. And so far, the best recommended technique is PCR, and we know that this is very time-consuming, and it requires centralized lab, and also it is expensive because the reagent and chemical that we use is expensive. But this is the best recommended technique so far. So there is an unmet need to develop some techniques that should be very effective in the field, like rapidly detect the things in the field and should be the cost effective. So suppose some app in the mobile, like we can take our cell phone to the field, we can take the images, we can take the spectra, and we can just detect, like, okay, this is the red blotch infection, or this is this infection. So we need this kind of technique. So we are trying to figure it out, and our hypothesis is when the leaf get these kind of infections or vine get these kind of infections, then definitely there is change in phenolic profile of the leaf, there is change in pigment and water content of the leaf, and there might be other structural compositional changes like maybe polysaccharide, maybe lignin, maybe other biopolymer. So if we can explore that which type of property is mostly infected by these kind of virus, then might be we can get some features that can give us a better classification between infected and non-infected leaves, as well as infected with the red blotch virus and other virus. And if we can explore those kind of features, then we can apply some deep learning or machine learning models, and we can develop some prototype device that can help us detecting even in the field very rapidly, and that will be the cost effective. So, and another hypothesis is nowadays it's very common. The people are working in these kind of fields like detecting disease in the leaves. So they are collecting a lot of images, and then they are applying some deep learning and machine learning models to have the detection of the diseases. So we are also exploring that field also. So we are collecting a lot of images, and we are thinking maybe on the image quality, we will be able to develop this kind of technique to detect the virus infection. So with this hypothesis, we plan that we can explore the compositional changes in the leaf using FTIR spectroscopy. And we know the FTIR spectroscopy is a very well-known spectroscopy to evaluate the changes in the compositions. We are also trying to explore data based on the NIR and hyperspectral imaging, because that can give us the information about the changes in the pigments and the water content. We are also collecting a lot of images, RGB images, and we are trying to run some model, some deep learning, machine learning model, and we are exploring if that can help us in developing this kind of instrument. So in case of compositional analysis using FTIR, we run the FTIR with the whole leaf, but the leaf has too many biopolymers, and then there is kind of overlapping of the peaks, so we were not able to distinguish a lot. So we decided, because these kind of infection, they affect the water content of the leaf, so might be they are affecting the water-soluble biopolymers. So we decided to extract the water-soluble component from the leaf, and then we analyze the compositional changes using FTIR. So in this talk, I'm just going to focus on FTIR and whatever the result we found so far based on the RGB images, because we have the limited time here. So we decided for the FTIR-based technique, we decided first to see the changes in very highly infected leaves. So for that, in 2020, we collected some samples from foothill region and at very later stage. So there we had like very infected and non-infected samples. And then we extracted the water-soluble polymer, and we run some FTIR to see how the compositions are different in infected and non-infected samples. So this is the, oops, sorry, it run, no. Okay, so this is the raw FTIR spectra, and in this, the 900 to 1400 per centimeter, this gives the carbohydrate region. The peaks in this region are the characteristic peaks for the carbohydrate in the FTIR spectral region, and these regions 1600 to 1650, this region contains the protein, and there are some other regions like a lipid and all these. But when we run the second derivative, so we were looking different sections like lipid section, protein, and some kind of carbohydrate sections. So we got that infected and non-infected leaves, they have very different carbohydrate profile. So there is huge differences in the polysaccharides and other monosaccharide in the infected and non-infected leaves. And here, this includes the CO stretching band. This definitely gives the information about the glycosidic linkage. And the glycosidic linkage is one of the markers for the polysaccharide. So So we got in the second derivative that there is a huge difference in the carbohydrate profile for infected and non-infected sample. And after that, we run the principal component analysis, and we got that this feature, the changes in the carbohydrate profile, is giving us a very good classification among the infected and non-infected samples. So the S is infected sample, and the C is our control sample. So after getting this information that compositional changes among these infected and non-infected leaves can give us the better classification, we started collecting a lot of data, and then we chose different locations and different time slots, different months to collect the samples. So here we chose 2 locations, one is Foothill and one is Napa, and we chose these locations because at one location the plants are neither irrigated nor grafted, and another location it's irrigated and grafted. So we wanted to have the varieties to see like if there are different varieties of the leaves, then how it's changing. Also, we collected the sample at very early stages like May and June, and also the later stages, September and October. We also cover in one, unfortunately we didn't get August sample, but we got July sample, and that defining somewhere at the mid stage. So for those samples collected in May from Foothill locations, we extracted the water-soluble polymer, and then we run the FTIR, and we did the principal component analysis. And here we can see that these features collected using FTIR spectra can classify the infected and non-infected sample at very early stages of the vines, that is May. And the same kind of separation, the classification we got for Foothill region at later stages too, because even at early stages we can find like classification. So at later stages, infections and symptoms are more pronounced, so we got a very good classification for Foothill region even starting from the early stage. So I'm not going to show all the data that we process for the Foothill region, but I'm going to show this one. So we also collected samples in May from the Napa region, and this is, as I told, it is irrigated and grafted. So here we run the same kind of analysis, and here we got that some of the negative samples, they are clustering together to the positive samples. So, and this thing we appeared in the spectral bands too. Here also we got that negative bands are overlapping to the positive bands. So that time we thought maybe this is irrigated and grafted, so maybe in these locations the leaves, the infected leaves are not showing that much differences, and that's why we are not getting the difference. But these samples at the later stage, so at the early stage too, it was the PCR was run to know that these are the infected and non-infected leaves. So at the early stage in the May, the sample was negative, but at the later stage in the July, the same sample from the same vine, the samples become the positive. So it means might be the FTIR is even more sensitive than PCR to detect the sample at very early stages that is not detected by the PCR. So this is kind of spectacular at that moment, but after this result, we are kind of at the stage that we can think that maybe the FTIR is the better tool. So, and then I process for other months, June, July, August, September, and October. So from the June, because here we can see that there is the classification of the infected and non-infected sample and this is kind of also early stage. But here we can see some of the positive that is not very far away from the negative. And this became more clear when I run the hierarchical median linkage clustering. And here we can see that some of the positive sample that is very little far away from the negative sample, and some of the positive is very far away from these negative samples. So there is clustering at the early stage, but might be at that stage, it's kind of maybe the leaves response is not that much difference. So we have some kind of overlapping, but still at the early stage, we are able to classify even irrigated grafted samples are nor irrigated, nor, neither irrigated nor grafted samples. And this we can see at the later stage, it's July. Here we can see still there is differences among the leaves. There is differences in the characteristic of the leaves. And that's why from the same positive sample, we can see there is some separation. And here in negative also, we can see some separation. But if we compare the whole negative and positive sample, we can see it's very far away from each other. So it's clustering very well. And in the September, we can see the differences among the leaves, because as it's going later stages, the characteristic of the infection is going, it's more pronounced, and now we are getting even in the among the leaves, there is less dissimilarities, but again, it's clustering very well, the negative and positive. The October data is similar to the September one, because we saw that during the characterization, I saw that the September, after September, there is not huge changes in the symptoms, because maybe the September is already a later stage for the kind of whole infection. So from this study, our overall take is the water-soluble polysaccharides are changing significantly in the infected and non-infected samples, and this might be a key descriptor to predict the infections in the leaf, the red blotch infections in the leaf. So our next goal is we are going to collect the data. We have already data, infected and non-infected sample with this infection, but we are also trying to collect data with other disease and combining with this and trying to apply some machine learning tool to detect the red blotch infection, even with comparing with the fresh samples or comparing with the other infected samples. So that's we are still working on. So next, I'm going to explain about the whatever we found with the image collection. So here also, I only worked with the later stage samples, because I wanted to see how my modeling is working and if up to what level I can get the prediction with my models. So here also, I'm working with the later stage samples, and that's why this is the fresh leaves and this is very infected leaves at the later stage. And then I'm applying some convolution neural network model, and I'm trying to predict the fresh leaves and the infected leaves. So this is my training data, and this row is fresh leaves, and this row is highly infected leaves. And I'm using some processing also to enlarge my data set, because I have the limited sample of imaging. But even with the limited samples of imaging, my models are working great. So that's good. So here I applied 3 kind of models. One is Inception V3, ResNet 50, and the sequential CNN model. So the first 2 is kind of transfer learning model, and it is already, this model is designed by Google and Microsoft, and it is designed after training on like 1 million of the images. So these kind of model already trained to extract a lot of features to give to the model. So I'm applying these two models, and then I'm also applying sequential CNN model. This is the simple CNN model. And this I got during running my samples, that the limitation with this kind of model is if my image size is 2048 and 2048. But if I'm running with those image size, then it's giving me a lot of parameters, and with that huge parameter, I need a lot of like a GPU kind of system to run those model. And for other one, even with this image size, my parameter is not that much, and that I can run the model even using the Google Colab that is freely available. So that's the limitations, and that's the advantage of these two models. So I have only 40 images for 2 classes, and I'm using my image size for these two is 2048, 2048. But here I have to reduce to 4. As I told, I was struggling with my GPU system. So I reduced the image size to 4, but I was confirmed that it's taking all the features that that is available in my infected and non-infected sample. So I confirmed those things, that it's not missing the features. So even I reduced the size, it was taking all the features. And then I run, so for these two models, I have to run only 2 epochs. Epochs is like my model run several times throughout the training data, like suppose 20 times. So it run 1 time, 2 times, 3 times, and then 20 times to better train on the data, and then on the test data, it gives me the prediction. So in these two models, I'm only, even with the 20 epochs, I can get very good accuracy, more than 90%. But here in the sequential CNN model, even using the 100 epochs, I can get the maximum accuracy 85%. I increase the epochs up to the 500, but there is no increment after that. So this is kind of very early stage. I'm trying so many models, and this is only tried on the images of the later stage, but I'm working on, I already collected the sample for the whole season, and I also collected the images in the field, and now I'm going to apply different models on those images, and I will see how this can be give me the better accuracy and better prediction. So these kind of work I'm working on. So I don't have like a real model to show, okay, this is the model and that is working, but I'm continuously working on to get at that position. And now I would like to acknowledge my team. So Christian, who presented before me, so he works with me, and we together collect the samples, and he run the PCR for me to let me know that this is infected and non-infected, and I run the all collect spectral data and run the modeling. And Dr. Sudarshana Masur, so he is our collaborator, and definitely without his help, we cannot do anything. And Professor Nitin, so he is my PI, he is there, and he gave me this opportunity to present my work here. Thank you for that. So, and finally, the USDA NIFA, they funded us to do this work. Thank you, and any question?
One question, excuse me, from online. Have you looked at red blotch spectra from white grape varieties?
Wild grape points?
So red blotch spectra from white grape varieties.
No, we didn't look the spectrum for white grape wine, but we are thinking that if we will have some model developed we will at the stage where we can explore like a different varieties, so then we will consider the white grape wine too. Yeah.
If I can add, changes we are seeing are in the carbohydrate region, which are So if I can add to that response, I think the changes we are seeing in the FTIR are in the carbohydrate region, so it doesn't have a color feature in there. So the features we are looking in the FTIR spectra are color blind, essentially, if you want to think about it. The features we are looking in the RGB images are susceptible to the color of the variety. So if you're looking for red versus white, we may find some differences there. But in the FTIR region, what we're looking at is the biochemical response of the plant to the viral infection. And I think earlier work from this group here as a team has shown that there is elevation in the sugar content accumulation in the leaves itself. So what we are finding is some of the polysaccharides or the monosaccharides are being tracked by the FTIR response in those cases. And we think that if the leaf physiology is similar to viral infection, that we expect to see very similar responses in different varieties of the vine in this case.
Anything else?
All right, well, thank you, Rewa.
Okay, thank you.
Okay, that brings us to